So we will continue. We're talking about frequency regulation, and we talk about a very specific problem, which is the issue of power balance. Help me here. What did we discuss?
Says that anytime there's a difference from, I guess, a deviation from nominal frequency, that goes wrong because generation is not matching load.
Mm-hmm.
So the bigger the deviation, the more bigger that power mismatch is. So that corresponds to power imbalance, and how we respond to that is the generators. Power drops a certain, when the frequency drops a certain amount, they have control systems to increase their mechanical power output.
Mm-hmm.
To respond to that.
Yeah. What is the role of inertia so far? What do you think?
As like a storage for kinetic energy, so that you have more time to react when you have it.
Okay. If you have a system with more inertia, why you are going to have more time to react?
Because the difference in power between generation and consumption, that is going to be chipping away at the kinetic energy in the machine. And so if there is less kinetic energy in the machine, then it's going to take less time for that same rate to bring it to instability.
So for the same power imbalance from generation and demand, for the same one, you might have a system with more inertia and another with less inertia. The amount of energy you might need is the same in both cases. But when you have more inertia, the sacrifice on the speed deviation will be less because you have more inertia. As you have mentioned several times during this class, your idea of inertia, that is a system that is resistant to changes, in this case, the frequency. So you have more rotating masses, more kinetic energy stored, and you can use that to cope with the imbalance instantaneously. So a system with more inertia, even if you have power imbalance, you will be able to provide that extra power you are missing from the kinetic energy, and the cost will be a tiny bit of frequency deviation. In another system, because we have a plot here, when the total inertia is smaller, then the deviation in the speed is going to be much larger, and that is a problem. We talk about what would happen in the future when we have new type of technologies. Let's think about solar PV plant, solar panels. In that case, you have a lot of new power you can use, but the issue with that, you don't have any energy stored in that component. So you will gain more power to satisfy your load, but you will not have enough of storage as you might have in a rotating machine, like synchronous machine. So that's a disadvantage. So in the future, we might face a scenario in which we might have large capacity, but we might not have the same amount of energy that today we store in the rotating mass. We talk, and this is just thinking, I don't have a clear answer, and there are many research these days that are exploring this. What would happen if the generation in the system is 100% based on inverters, new technology that do not involve synchronous generator? What would be the problem? What is the main problem? We talked briefly about that. The main problem is exactly the same. What is the problem? We need to match the demand. If you have a demand in the system, you need to somehow provide that power to balance that demand. Maybe this issue will be manifested in a different fashion, not through frequency. The frequency maybe might be controlled from the converter, I guess. But at the end, you will have the same issue. How you're going to balance that? And the only answer that I have is energy storage. So no matter in that futuristic scenario, based on new technology, we still have the same problem. Today, in a synchronized system, this is manifested through frequency. So whenever you have an imbalance, we see it immediately through the frequency. And because the system is synchronized, You don't need any special communication system to make the generator talks to each other, because everything is coordinated to the same frequency you have in the grid. That's why we have this massive system that was created more than a century ago and it's still working fine because of the synchronized system. In the future, then, if everything goes with generator based on converter, you will have the same issue. How we supply the demand, you need to match it. And maybe it will not be called frequency problem, might be called something else, but the same power balance problem we will have in that situation. Let's go back to the system we were talking. One way to deal with this power imbalance, let's think in the case you have more load than generation, then you need to move the generation from your generators and increase it. And the option is, are we going to increase them all in the same amount of power? And the answer was no, that's not smart, because you might have different type of technologies. You might have generators that can respond fast, or as David mentioned, it depends on the capacity that we have. And there is a term that I probably was not very precise, that we call it the power reserve. And one of them is the spinning reserve. So if you have a generator that will have a minimum and maximum power in some range, and the generator is operating at some point, then this margin that you have from the current operating point to the maximum power, that is going to be the spinning reserve related to the generator. Because this generator is synchronized with the system, is connected, then we can increase the power all the way from that point to the maximum point. How PJM call this? There. The primary reserve, but more precisely, the synchronized reserve. Yeah? So that has to do with this. What is the margin you have? You have a generator operating at a given power level. What is the difference with the maximum that this generator can provide? That's going to be the reserve of that particular generator, the spinning reserve. You sum these for all the generator, and you have a total amount of what the system can handle for a given operating point. Now, we recognize that this generator might have different characteristics, different technologies. They might be able to change faster or slower this power. You might have a gas turbine that might be able to change this power very quickly. Or you might have a coal power plant that might take more time to change the power. And you need to distinguish that. And how we're going to distinguish how much a generator can provide is going to be through the frequency regulation, more specifically through the Droop characteristic. So in that plot, I have an operating point. You have the power P0 is the power generated by this machine. And we're assuming that at that point, we have nominal frequency. The frequency is 1 per unit, 60 hertz. Now, if there is a power imbalance and you want this generator to produce more power, let's assume that that power now is going to be P1. Why you need to provide more power? Because the frequency in the system is going down. So the question is how we're going to move from the first operating point to the second, in which you need to increase the power production from that generator. How we're going to do it? We're going to do it with this Droop characteristic. The Droop basically has to do with this inverse characteristic, this linear negative slope. By definition, I like to always try to find the definition of words that I am not used to. And for this case, I don't know if you're used to the word droop. What is droop? But there is the definition. Basically, is describing this negative slope in that plane, PF. So this invert characteristic is known as droop, and the slope is going to be the characteristic we will assign to different generators. When you don't have this characteristic and you have a stiff behavior, then that slope is going to be infinite. That means that even if the frequency drop, the power output of that generator will not change and will remain at P0. So if you have a very large slope, that means that that generator will not change much the power, right? So if this slope starts becoming closer to zero, much smaller in absolute value, they're more flat, that means that the generator can respond fast and will be able to adjust the power output to cope with that power imbalance, okay? So in practice, this slope, because the power in frequency are in per unit, that slope is going to be in per unit as well. So if the slope is, we typically might think that the slope is 5%. In per unit, it will be 0.05, right? That's a typical value we assume. But if you have a generator that can actually adjust easily the power output in the event of a power imbalance, then that value can go to 2%, 0.02. Those are typical values. If you have a generator that is much slower and cannot adjust the power that easily, we might have a slope of 0.1, 10%. So that's might be the typical range for this Droop characteristic. That slope, RD, is called the speed regulation constant. By looking at the slope characteristic here, RD in absolute value is nothing else than this side divided by this side of that triangle, right? But if we consider the negative slope, then we can define this as the negative of P1 minus P0 divided by F1 minus F0 divided by P1 minus P0, if you want to consider the negative of the slope. Well, that slope is written here. And by algebra, we can isolate for P1. Basically, we send this to the other side. P1 minus P0 is equal to the frequency difference, F0 minus F1, divided by RD, which is what we have here. And then we can isolate for P1, we send P0 to the other side, and you get this characteristic. Why do I go through this equation? Because we will see this equation in most of the control scheme we have for frequency. What do we have here? You have an initial power for that generator, P0. This can be a set point for the generator. You know how much the generator needs to produce when you're at nominal frequency. But if there is a frequency change, then you will correct that value, so the generator will be able to produce P1 in that event. So if the frequency is less than F0, F1 is less than F0, this is going to be negative, with that negative will be positive, and the power output of that generator will move from P0 plus whatever delta power this will dictate. So that's basically the Droop characteristic. And remember this equation. We will see this equation as we continue describing the frequency control. So RD is the speed regulation constant. This is the case of 5% of the speed regulation constant, or 0.05 in per unit. So what is the meaning? Why we like to put this in per unit or in percentage like that? Because this will be a practical, will give you a practical idea. So in this case, imagine that the generator is injecting zero power at nominal frequency. So having this speed regulation constant at 5% means that the frequency needs to drop 5% so the generator moves from 0 to nominal power. So that's the mean. So 5% of speed regulation constant, then we need a speed deviation of 5% for the generator to inject nothing to nominal power. Of course, we have the 2%, which is going to be demanding more for the generator, because in this case, we will need just a deviation of the speed of 2% for the generator to go from 0 to nominal power. So these are going to be the generator that can have the capacity to do that and can respond with a relatively fast speed to increase the power. Are you with me? You understand what is the speed regulation constant? Yeah. So here we had been talking just at the about the speed regulation constant and the droop characteristic. But what about if we have now two generators connected to the system? Because this is a synchronized system, the frequency in a steady state for the two generators will be exactly the same. So in that case, we have the nominal frequency, F0, 1 per unit, 60 hertz. And in that case, the power generated is indicated there, PG1 and PG2, 0 at the initial point. If we ignore losses, the sum of the two power will give you the total load in the system, all right? So that's the condition at the system right now. But what about if there is a disturbance? Now, we have a change in the load, and let's assume for simplicity that the load is increased. If that happened in the system, then the power from generator 1 and 2 need to be increased, and we're going to increase it according to the speed regulation constant. In one case, we have a speed regulation constant for generator 1 that is much larger than generator 2. So which generator will be able to increase more power for this power imbalance? Generator 2, because the speed regulation constant is smaller. We need to remember, don't forget this, the system is a synchronized system. So in a steady state, if there is an increase in the power, in a steady state, the frequency for the two generators will be the same. So we have an increase in the load, the frequency will be the same for the two generators, and through this characteristic, we should be able to determine how much is the increase in the power in the two generators. So you can see in the plot the power indicated in blue. Yeah. The frequency chain, delta F, is going to be negative in this case, but it's the same for both generators because we have a synchronized system. In this case, because the frequency will be negative here, and then the idea is how we determine PG1 new, PG2 new, when you have the load from the initial point plus delta P, we're increasing the load. Then what we can do here, we can use this linear characteristic. How much is going to be the new power for the generator 1? Exactly what we described before. It's going to be the power at the initial point minus that delta F divided by the speed regulation constant. Delta F in this case is negative. So PG1 is going to increase from that 0 value to the new value because the delta F is negative here. Now the same thing will occur for the other generator. In this case, this speed regulation constant is going to be much smaller. And therefore, the increase in the power for this generator will be much larger. So as you can see here, because we're setting different speed regulation constant, the load sharing for this generator will be different. That generator that has a smaller speed regulation constant will increase more the power. So let's calculate, let's do some calculation here and see what we can get as an example. So we will have here two generators. And let's put some numbers. So here is going to be the frequency, initial frequency, which is going to be 1 per unit. And here we're going to have some power. Let's say this is 100 MVA. Let's work with this in per unit. Let's say this is 1 per unit. This is the power of generator 1. And for this one, we can assume any other value. Let's say this is 1.5 per unit. This is the power from generator 2. And we're going to consider a different characteristic here. So for one, we're going to use some speed regulation constant. And for simplification, let's assume that this is 5%. And for another, we're going to use a different speed regulation constant. And for simplification here, let's assume that this speed regulation constant is 0.08 per unit. 8%, 5%. Now, the total power in the initial case, you have PG1 0 plus PG2 0. It's going to be, in this case, 2.5 per unit. And this is going to be the total load we have in the system. But if there is a change in the power, now the load is increased 0.5 per unit. So it will move from 2.5 to 3 per unit. Then the question is, how much the power in these two generators need to be modified? So we need to increase in total 0.5. Is it going to be equal? It's not going to be equal. And by the description that we have so far, this generator 1 need to take a larger share of that increase of power we need. So how are we going to determine this? What is the key to solve this problem? We have all the information. We have the speed regulation constant. We have the initial point, and we have a load increase. How can we determine or solve this problem? Perfect. Perfect. And why we can do that? Because this is a synchronized system. The frequency for both of them need to be the same. So here, graphically, maybe we can solve this. The frequency will be the same. So in that case, this is the increase in generator 2. This is the increase in generator 1. This is much larger than this one. So here, basically, we need to determine first how much is the deviation in the frequency. There must be a deviation in frequency that will lead exactly to 0.5 per unit increase in the total generation. So this value plus this value need to be equal to 0.5. So that's what we're going to do now. So how much is going to be delta power in generator 1? How much is that going to be? Delta F over RD1. How much is delta F in this case? Negative. So we need to put a negative there because we know that that will imply an increase in the power. Or the generator 2, delta F divided by RD2 is the same frequency. It's a synchronized system. So from here, we get delta PG1 plus delta PG2, which is going to be negative delta F, RD1 negative delta F over RD2 must be equal to the increase in the load, which in this case is 0.5 per unit. So from this equation, we can determine how much is delta F. Yeah, Uh, so we have here delta F is going to be 0.5 negative divided by this one. That expression. Okay? So we can calculate that. 0.5. 1 over RD1, that is 20, right? And then 1 over 0.08 is going to be 12.5. So what we have here is negative 0.5 divided by 20 plus 12.5. And that leads to negative 0.0154 per unit. So with that, we have determined how much the frequency drop for this system when the load is increased 0.5 per unit. Is there anything we can do to improve this? Maybe we're not happy with that increase in the demand and this delta frequency is too large for us. What can we do? Add more generator. What about if we just have these two? We need to figure it out whether the generators, they have enough capacity so we can increase the speed regulation constant in both of them. Whether they have capacity and whether they can respond fast enough to increase that power. If that is the case, then we're not happy with this. Let's tweak this a little bit. We need to make them smaller, yeah? And then they will respond with more power or less deviation in the frequency. When you have that frequency that is determined here, all that we need to do to replace it here, and we determine how much is the power that we need to increase from each generator. So for generator 1, it's going to be this value, the negative of the delta frequency, divided by the speed regulation constant of the first generator. And that is about 0.308 per unit. And for the other generator, we use the same frequency and the other time constant, speed regulation constant. And then we have 0.192 per unit. So with the speed regulation constant, basically, we are defining how the generator will share the load. If there is an increase or decrease of the load, how they're going to adjust that power to balance against the demand. Is that clear? Yeah? Okay. I want you to not forget this relationship. This relationship will show up in the controller we will see very soon for the frequency. And as you can see here, this generator can be located in different parts of the system. But because it's a synchronized system, we don't need any communication whatsoever. Yeah? So the only signal to coordinate this control is the same frequency of the grid. So we use a signal that is in the grid to do this control. That's why this was so effective. That's why this was built more than a century ago and it worked to coordinate the generation in different parts of the country. Now, if we have a system that is based purely on inverters, do we need a communication system? I would say yes, we might need that. That might be a drawback, I guess. I don't know. That's not my expertise, power electronics, but I don't think we can have a signal that we can use in the system in that case to coordinate controllers. So we might rely on a good communication system in that case. Well, the power grid as it is today, we use the same frequency of the grid. Yeah, so when you control this, the power is increased, in this case, 0.5 per unit. And the generator 1 and 2 need to increase their generation. But now the new operating point for the frequency is going to be this one here, which is 1 minus this volume per unit, right? What about if we're not happy with that frequency? We need to increase the frequency and restore it back to 60 hertz, back to 1 per unit. So in that case, we use what we call the secondary frequency regulation. This is the primary frequency regulation. Any change that we have in terms of load, generators will increase the power with a cost. And the cost is, in this case, because you're increasing the demand, the cost is a reduction in the frequency. But if we want to fix this problem and we want to take the frequency back to 1 per unit, the nominal frequency, we need to do something. And that something is the secondary frequency control. So what is the meaning in that case in terms of this plot here? Basically, what we have to do in this characteristic, we're going to pick one generator that will be able to do the secondary frequency control. Typically, secondary frequency control will take more time. This will be done over several minutes. It's not immediate as the primary frequency regulation. Primary frequency regulation might take several seconds, maybe up to a minute in very slow system. Several seconds, but the secondary frequency regulation will take several minutes. And because it's a much larger time that we have, longer time, then we can use other type of generators that are not very fast to respond, but they can increase over some period of time their power output. So we will use those generators to provide some secondary frequency regulation if needed. So what is the purpose here? So you will have an increase of 0.5 per unit in this example. So what you're going to do, basically this characteristic need to be pushed to the right in this description, graphical description. So let me erase this. So if we display this characteristic to the right here, for the same frequency, what will happen? You're making this generator to go beyond the power that we need to balance the load. So if you move in that direction, what will happen? You will have more generation than load, right? What will happen to the frequency? The frequency will go up. So you will push this to the right in a way that the new operating point is somewhere here. So this generator here will be providing the new 2' value of power. So basically, this is going to be 0.5. So this generator will be in charge now to inject all the power related to that load increase. And if that is the case, then this generator will go back to the original operating point. So there is a generator that might take more time to increase that power output over several minutes to take the increase in the load and to restore the frequency in the system. So that is the case of the secondary frequency regulation, and that is what I have in the slide. So we need to modify this characteristic. You remember the equation. I said, remember this equation, the equation from the Droop characteristic. Let me put it back here. Let's use this other one, this one. What do we need to do here in this characteristic to make the secondary frequency regulation? So you will have here delta frequency. But here you have an initial set point for the power output of the generator. So basically what we have to do in this characteristic, basically we need to increase over a period of several minutes, because we need to leave some time for the generator to respond. We're going to change this P0, that is going to be the new set point for that generator that is doing secondary frequency regulation. So if this generator produces that increase, completely that increase in power in the system, all the rest of the generator will go back to the previous set point of power. Do you think we will like to do that? That all generators go back to the initial set point for power? Yes or no? How do we determine this? I guess that we need some economical consideration. The initial operating point is given by a power dispatch. It's a combination of power from all the generators that will minimize the cost. So if we have secondary frequency regulation, we need to keep that in mind. So if you have just one generator doing secondary frequency control, you might deviate from that optimal economical point for the power dispatch from the generator. Yeah? But you don't have to have just one generator doing this. You might apply this in other generators as well. All right. In this, we had a term, and that I introduced this term before, and we call it the governor. Last class, I said, I don't know where this term came from. And the term came from mechanical design. With the revolution of the steam machine in 2 centuries ago. And the governor basically is a device, as you can see here. I cannot read all the parts, but it's an engineering concept that defined through bulbs and pipelines with the steam, for example, that can make adjustment of the control of a bulb that can inject more or less steam, in this case for the generator. So it's a device that automatically will regulate this if you have, for example, in the generator, a decrease in the speed. What is the mechanism we need to implement through this governor? Is an increase in the power. So all these pieces here are supposed to do that. I tried to look at this. There is a document which is here from 1930. You can take a look at that and read it. But to me, that looked like very complicated, right? Did you watch that cartoon? Poor guy. I always wish that now you're going to get it, and he was never able to get it. But unlike this poor coyote, this machine actually works. If you go to an old power plant, probably you will see all these pieces and the governor and how these valves are adjusted based on the frequency that you might have in the system. Very creative, very creative. But we're going to study one that is more simple. Yeah, we don't want to make it too complicated like the one from the previous picture. And this is a more simplified version of that governor. And this is obtained from the book of my PhD advisor, Professor Pete Sauer. So in this configuration, as you can see here, we have a valve. This will control the flow of steam that will be sent to the turbine. If this piston is moved down, then you will have more flow. If you have more flow of steam, what do you expect? More power. the opposite is true too. If you push this thing up, then you will close the valve somehow. You will reduce the steam flow, and then you will produce less power. In this system, you see here a flyball, speed governor. Basically, this has a spring that has some characteristic, K characteristic of the force, and how much will deviate for a given speed. The faster this rotates, this ball will move to the side. And if the flyball starts spinning faster here, this will be pushed to the right here, to the left, and this part is going to be moved down, right? Consider this part here. This is a speed changer. It can reduce the speed or increase the speed if we move this up and down. Let's consider that a manual control. Let's assume that that is the exact position we have for this machine, and the machine is with a given steam flow producing a certain amount of power. Let's assume this point is fixed. Now, because we're operating at nominal condition, let's assume now that there is an increase in the power demand. What will happen if there is an increase in the power demand? The machine need to provide that power. Where that power will come from? The kinetic energy. Through the kinetic energy, they will reduce the speed some. So for this particular generator, the balls are not going to spin that fast. They're going to get much closer. If they get much closer, that point B will be raised. This is manual adjusted, and it's fixed at this point. So if this point is fixed and B is increased because the frequency got reduced, what happened with the point C? Got increased too. Point A is fixed because it's manual. Point B increased because the balls are closer. C will be increased. At that point, let's assume that this piston has not moved yet. If this piston has not moved yet, if C is increased, what happened with B? Will be increased, will be pushed up, right? It's pushed up. If the point D is pushed up, look here, you have high pressure oil going here. In the initial operating point, the oil was not going nowhere. But if this is pushed up, where the oil will go? Through the top part. The top part will be filled with this oil at high pressure and will push the piston down. And if the piston is down, you will have more steam going through the turbine and more power. The opposite is true too. If for some reason the ball are separated because this is spinning much faster, there is a generator outage, then point B will go down, C will go down, D will go down. And in that case, the pressure will fill the bottom part of the piston and push the piston up and close a little bit that valve, and less steam will go to the turbine, less power. So that's the primary frequency regulation that we discussed, and that is the action of the governor. Yeah, are you with me? Last part, we want to do secondary frequency regulation. What do we need to do? Intentionally, we want to pick those generators in charge of secondary frequency regulation and increase the power beyond the value that we get from the primary frequency regulation, beyond this point. So for that, we need to push this characteristic to the left, to the right. How are we going to do that? With this manual adjustment. So if you wanna, let's assume that the frequency went down, this point B and C went up, D went up, and the piston was pushed down. We're producing more power. But now if you wanna restore the frequency, what do we need to do? We wanna increase the frequency. The frequency went down, this point B went up. If you want to increase the frequency in the system, what do you need to do? Inject more power, right? So in this case, we need to push this down a little bit more, right? If you push this down, the frequency will not change immediately. So the same thing will happen here. Now, B is fixed. The point B is fixed. If A go down because we're making that adjustment, point C will go up again. And the same process will be repeated. D, the piston will not change immediately, so then D will be pushed up. More oil will go in the top part of the piston, and we will open the valve even more, letting more steam coming out of that machine, more power generated, and that should restore the frequency. As this is taking in more power, the generator from the other power, as the frequency is going to be increased, the generator in the other machine should move down because of the speed regulation. Yeah. So this is the governor. Yeah. Now to finalize this part, we talk about the primary frequency regulation, secondary frequency regulation. We talk at the speed regulation constant. We talk about the correction of the power set point. Now, the last part to understand this is to describe the turbines. Not all synchronous generator will use the same type of turbines. You have hydro turbines, like the one in the figure. So in this case, we need to describe how the turbine will behave. And the behavior here for this type of power plant is very complex, non-linear, because you have a mass of water that in this case will go from upper dam, will go down to that penstock and will hit a turbine that will start rotating. But the dynamics here are way more than non-linear that you might experience in a steam power plant. But still, we can come up with some representation, and we need to know how fast or how dynamically this turbine might behave when we start controlling a gate or a valve that will control the flow of water that will hit the turbine. Yeah. In this case, here you have some equation here. The water speed here will be proportional to the gate position. So that's what we control, how much flow we let pass, and depend on the square root of the hydraulic head at the gate. So you measure this from the top of the upper dam, the level of the water, and you measure that with the bottom part of the turbine. So if this is higher, then the water speed will be higher as well, and then you will be able to produce more power. In the country, we don't have a big percentage of hydro power plant. What is the percentage? Do you remember? About 7%. Around 7%. And the other one is the steam turbines. So the steam turbines, we have two types, and I'm going to finish with this first part. One in which you have just one shaft. In this shaft, you might have different type of turbine. A turbine that works at high pressure, then a turbine that works at intermediate pressure and low pressure. They're all connected to the same shaft in tandem, and that is connected finally to the shaft of the generator. So we're going to leave it until here, but basically we're going to finish this part describing turbine and how we can describe a turbine like this. And we're going to use a model and then understand how we can use that model in the dynamic representation of the system. And that's going to be the kind of the last part that we're going to discuss this semester. Okay? Thank you, guys. Is there any question? Any question?
Yeah, so in secondary frequency control, so if one generator goes beyond the nominal power, basically, so its frequency, you're going to want to increase. what happens after that? Does that have to go back down again? 'Cause then
If you go beyond nominal power, you cannot go beyond nominal power in a generator. From the
it
in,
increases the power to, so you have more generation than demand, to get the
Right, right.
frequency back to nominal frequency.
so one gener
Now that there's more generation than demand, when does that have to come back down again?
right, because when the frequencies start increasing, being restored, the other generator that you are not acting on the other generator, the other still have the original set point. The other will start decreasing the power because of the speed regulation constant. So while you increase the power with one generator, the other decrease, and to maintain the balance. Yeah, yeah.
And that'll get the frequency
Back to 1 per unit. Yes, but this will happen over several minutes. It's not going to be at the same time than the primary frequency regulation is occurring. Yeah. Thank you, guys.